In this video, we're going to talk about the chain rule, which is what we call it when we take the derivative of a composite function. A composite function is something where we have like an inner function and an outer function. So we have this cute little cartoon over here. It says we differentiate the mother, leave the baby inside, and then we differentiate the baby. So if you hear me talk about baby, I'm talking about the inner function. And we have an inner function anytime x is inside anything other than an exponent. So here x is not really inside because it just has an exponent. That's fine. Trig functions should have just an x. Natural exponents should have just an x. So all of these are not composite functions, therefore they do not require the chain rule. On the right hand side, x is inside a radical. So it's an inside, the x squared plus 1 is the inner function. Here, trig is supposed to just have an x. When it has something else, all of that is inside of sine. So that's a composite function with 6x and sine of x. In the next one, again, 3x plus 2 is inside parentheses. So all of that is to the 5th power. That's a composite function. And then in the last example here, x squared is all inside of tangent. So on the right, we would have to use chain rule. And what we do is we take the derivative of the outer function, that's like the mom in the cartoon, and then we leave the baby inside. We leave that inside function alone, and then we take its derivative, and we just kind of stick it on the end there as a multiplication problem. That's kind of why it's called the chain. We start by taking the derivative of f, and then we bring that derivative of the inside function to the right. Remember, we can only take the derivative of one thing at a time. So that's kind of why we take the derivative of f, but not what's inside, and then we take the derivative of what's inside. So for our first example, here we have our inner function. Our outer function is basically like x to the 3rd. So we take the derivative of the outside first. So imagine that what's here highlighted is just an x. So if that was like y equals x cubed. Okay, this is all that stuff in the parentheses. So we bring the 3 down. We're going to bring this 3 down. But we leave that baby, we leave that inner function inside. So I'm going to leave the x squared plus 1 inside. And then we always subtract 1 from our original exponent. So it's going to be to the 2nd. So the derivative of this would have been 3x squared. We should kind of see that outline right here. Once we do that, then since we haven't taken the derivative of this piece, now we take the derivative of that, which in this case is just 2x. And this is called the chain rule. So when we have the derivative of a natural logarithm, it's just 1 over x. Again, if this is anything other than just an x, then we do have to apply the chain rule. Absolute value functions, I don't see a lot, but if we are supposed to do that, whatever function is in here, we carry over, then we multiply by its derivative, and it's all over the absolute value of the denominator. So, for example, the derivative of ln of baby is 1 over baby. And so again, I'm just kind of looking here, thinking of this as 1 over baby, 1 over whatever this is, and then if this is not an x, then we need to multiply by its derivative and apply the chain rule. So here, ln of baby is going to be 1 over baby, or 1 over that inner function, times the derivative of whatever that baby is. And in this case, the derivative of that inner function is 2x. So sometimes we do need to rewrite before differentiating. This guy right here would require the chain rule twice. We don't want to do that if we don't have to. So here we can rewrite this as x squared minus 1 squared all to the 1/3 power. And again, we still have the chain rule twice. We have this inner function inside the squared, and then this is also an inner function. So we want to avoid that if we can. So we simplify. Here when we have a power to a power, we multiply those powers. So my original function is really equal to x squared minus 1 all to the 2/3 power. Now it's set up that I only have to use the chain rule once. So the derivative then would be 2/3. That inner function stays put. Again, I can only take the derivative of one thing at a time. And right now I'm taking the derivative of this outside kind of mother. So if I subtract 1 from my exponent, I get negative 1/3. And then since I still haven't taken the derivative of this inside piece yet, I then multiply by its derivative. And we'll work on simplifying those later. So here we are going to have the chain rule twice, and there's no way to avoid it because we have a trig function. So we still need to rewrite it. We need to write it as the cosine of 2x. So both of these are inside the cosine, and that's all to the 1/2 power. So this one's going to get pretty ugly. So when we take our derivative, again, we have to kind of look for the inner function. So here's our inner function. So right now we're just taking the derivative of everything outside. So my 1/2 comes out front. This whole blue square, that baby, stays inside. So it's cosine of 2x, all now to the negative 1/2 because I subtract 1 from that exponent. So that's the derivative of the outside. Now I need to take the derivative of this blue box here. And the blue box also kind of has a baby because all of that is inside the cosine. So the way we kind of say this is, I mean, it's not really said this way, but I say it as cosine of baby turns into negative sine of baby. It's really important that whatever that inner function is, stays. Then we take its derivative. So we never have differentiated this 2x yet, so now we multiply by its derivative. And that would be the derivative then of that function. And here's just a summary of all the different rules. The trig ones that I think that you should memorize are going to be sine, cosine, tangent, and secant. These guys are pretty easy to remember. These are all like the chain rules. So if this is just an x, then we don't have to worry about this piece at the end. And if it is, its derivative is 1. So you can always think of it if you want to. This guy is not very common at all. This one's starting to be on the AP test a little bit. These two are very common. And then obviously everything in this whole column, all of these are very common in that one. And that's it.